out. I corrected, okay? So I corrected the thing. It's a mistake in the implicit function theorem. The statement of one of the question was off. Now I think it should be doable. I don't know if you've tried it. I did it this morning. So again, now it should become standard. But I think you have a 3 by 3 determinant to compute, right? Yeah. I think it's not a bad one. Okay, so you know how to do 3 by 3 determinants, do you? Yeah, okay. Linear algebra, you should be able to do that. I don't, yeah, okay. Great. So let's continue where last time we saw a change of variable, the change of variables to 2D. Now we'll move on to 3D integrals, okay? Now we'll move on to triple integrals. Okay, and I also posted quiz 4, I think, this morning. I don't know if it's up here. I posted it. So when do you guys want them due? You want them due on Monday or on Friday? Monday? Monday, sure. I'll make them due on Monday. So I'll technically make them due on Friday and then extend it for everybody until Monday with no penalty. Okay? These are just so that we abide by the rules. I think I'm not allowed to give you something due. I mean, I can make it due Thursday and then extend it with no penalty. Is that fine? Okay, so I'll do that. And yeah, sure. I mean, technically, I'm not allowed to assign anything, I think, past this Friday. So what we'll do, we're gonna make it due this Thursday, and then extend it, you know, unofficially give you a free extension. Okay, that way you can work on it. Okay, great. So any questions on the things we have done last time? No questions? Great. Let's move on to triple integrals. So the motivation behind triple integrals is the same as the integrals, almost. And the idea is that, any questions? No? Great. So consider A, B, C, D, E, F is bad. This is bad. In our cube. And suppose F is continuous on AB cross CD cross SD. Then what? Then triple integral. Sorry, SD here. Fx y z. Let's say dz dx dy. What is that? CD. Equals one more. Let's flip the order of integration. Where do you want to flip? Well, and you can flip it the way we want, right? How many flips you can do here? 6, right? You can do 6 flips, no? Yeah? Anyways, so flip it the way you want, and so on. This is really a triple integral. Now the motivation is really exactly the same thing as a double integral. And let's start with a small example to calculate. An example from the book to calculate a triple integral. An example from the book. Integrate book, but anyways. And say 0.4. How do you integrate this? Everybody, how do you integrate this? We all know how to integrate this or not? Just the most obvious way. Okay? You integrate this the most obvious way. Okay? Should I integrate it or not? Or that's fine. It's good? Great. Now one way you notice it's a rectangle, right? It's a box. And I have a product of three functions. What can I do with the three integrals? I can just split them here. I can split them. So x is just x goes from where to where? From 0 to 3. Y goes from 0 to 2. Y goes from 0 to 4, sorry. And z goes from 0 to z goes from 0 to 2. Z. Now you can evaluate it this way. So what do you get? You get e to the 3 minus 1 times y squared over 2. So 4 squared over 2, this is 8, and times z squared over 2, 2 squared over 2 times 2. So you get 16. Let's do more interesting examples just by calculating integrals. So evaluate 0, 1, 0, 2. Let's say 2x minus y is dx, dy, dz. Making sure that I got the balance correct. Y minus z squared 2. Yeah? Okay. Great. How do I evaluate this? It's easy, right? Do you see how to evaluate this? So when I integrate with respect to x, y is constant. Great. So I can split this, or I can just do it like that. 0 to 0 z squared. So and derivative of x, 2x is x squared minus yx from x is equal to y minus z, and x is equal to 0 dy dz. So let's see what we get. Y minus z squared, so integral. I messed up. Integral from 0 to 2. Integral from 0 to z squared. Y minus z squared minus y is y minus z dy dz. And then we integrate. So let's see if we can factor y minus z out if we get something nice. I don't think so, but let's see. Y minus z minus, oh we do, minus y, right? So really, in 3D, it's just an extension of 2D integrals, and all the nice theorems will hold. Okay, you can flip the order of integration on a square, and you evaluate the integral by iteration. So let's do that. So it's clear that if I factor a y minus z out, I get y minus z times minus z. Is that clear? You see that? You cancel the y squared, right? So you get y minus z times y minus z minus 1. So yeah. So you get the 0 to z squared. What is my bound? What is my bound? Y minus z times y, right? It's minus y. Is it minus y? Y, no, it's minus z. Y, z. And now you can integrate this, right? Let's double check. Y minus z times y minus z minus y. Yeah. So how do you integrate that? Z is constant. So 0 to minus z, y minus z. What's the next derivative of that? It's minus z times y minus z squared over 2 from y is equal to z squared to y is equal to 0. Is that right? Is that good? Yeah. dz. And then how do I integrate that? So it's z squared minus z. Okay, now it's clear to integrate this, right? Did I make a mistake somewhere? Are we following? Yes?
I didn't understand how you went from the last line
to here? Factor y minus z out. Y minus z times y minus z minus y. So it's y minus z times minus z. Sorry. Okay? Are we following? Is the integration correct? You know, it's going to look maybe ugly. Hopefully not very much. So 0 to 2, z squared minus z, oh man. Okay, so I have minus here. Z and z squared minus z squared minus z squared over 2. Is that good? Is that good, guys? Did you guys try it? Is that fine? Now how you can do this, you can just a squared minus b squared, right? You may get rid of things. Or you can just integrate this. I mean, I won't integrate that. That's easy to integrate, right? Worst case scenario, what do? Expand the square, and this is just a polynomial, okay? Expand everything and integrate. Yeah? Great. Finish this. Unless I messed up somewhere, but this is really the triple integral, okay? Just slightly different than double integral in the sense that you have one more integral that you have to take into account. Great. Now, we do one more example, or that's actually good? Is that fine? Actually, is that fine? Or we do one more? We do one more? Yeah, let's do one more from the book. 6xy dz dx dy. Zero from z to 0x plus y to 2y, 0 to 1. Let's do this. 6xy, when you integrate 6xy with respect to z, what do you get? What is 6xy with respect to z? Constant. So when you integrate that, what do you get? You get integral from 0 to 1. Y to 2y. 6xy z, so you get 6xy times x plus y dy dx. Now you know how to integrate this, don't you? So you, no, it's dx dy, sorry. You know how to integrate this, right? We know how to integrate that? Yes or no? Yes, this is a 2D integral. Let's do this. So I mean, we need to find antiderivative with respect to x. So it's 0 to 1. I'll take the 6y out. And you get x squared plus xy, right? So you get x squared over 2 plus, so you get x squared over 2. Or you get, well, let's give it x squared over 2 plus xy squared, right? No, I took the y out, plus xy. So you get, so x squared, so x cubed over 2 plus 6xy, so you get x squared over 2y. From x is equal to 2y, x equal to y dy. 0 to 1. So you get 2y cubed, which is 8y cubed over 3 plus 4y squared times 2. Okay, so it's 4y squared times y, so it's 4 times 2y, so it's 8y cubed divided by 2 minus y cubed over 3 minus y cubed over 2 dy. 0 to 1, what do you get? 7y cubed over 3, so 6y times 7y cubed over 3 minus 7y cubed weird, actually. Oh no, that's fine, that's fine. No, it's a bit weird. There's something wrong, right? Is there a mistake somewhere?
I think the second fraction.
The second fraction. Here?
Yeah.
Here, let's see. It's 4y squared, so it's 4y cubed, right? Thank you. You can catch a mistake. Why did I catch a mistake? How did I know there was a mistake? Immediately I looked at it and said, there's something wrong, right? How did I know? Without knowing that there's a mistake. Without knowing where the mistake is, I immediately looked at it and said, there's a mistake. This function is positive on this region. You agree? You agree that z is positive, y is positive, so x is positive. You agree with this? And this function is hence positive on this region. So my answer must be positive. Now if I had 7y cubed minus 7y squared, so I get y cubed over 3 minus y cubed over 2. That's a negative. Positive, negative, I'll get a negative answer. Okay? So it's always good to check whether your answer makes sense. If I tell you find the volume and you get an answer of negative 10, you know that that's wrong, right? Great, so let's do this. So it's 7 cubed minus 3y cubed, so it's 14 minus 9, right? So it's 5y cubed over 6. Oh, that's nice. 6y. 5y cubed over 6 dy. So what do you get? 5y4, right? Is that good? Yeah. So 2 times 7 is 14. 3 times 3 is 9. 14 minus 9 is 5 over 6 dy. 5y4 dy, so you get y5, right? Well, so you just get 1, right? Well, y5 from 1 to 0. Is that what you got? Yeah? Yes, sir.
Shouldn't be plus dy cubed over 2.
Oh, shoot. Thank you. Oh, man. That's going to be bad. The other one would have been nicer. 14 plus 9, 23. Right? 14 plus 9 is 23. 23 over 5, right? You get 23 over 5. Is that what you got? Okay, thank you. Yeah? So 14 plus 9, just put on the same denominator, you get 23. 23 over 6. Great. Should we do one more, or that's fine? We do one more? We do one more? Let's do one more. Oh man, that's gonna look bad. Z integrate. I'll erase here. Can I erase here? Everybody, can I erase here? Yeah? Let's integrate 0 square root 1 minus z squared 0 1 0 1. Let's see what's the function. Z sin x dy dz dx. So how do I start by integrating? Z sin x with respect to y is a, everybody is a constant. So how do I integrate that? This is 0, 1, 0, 1. You integrate with respect to y, you get square root 1 minus z squared z sin x dz. What do I have here in 2D? In the zx, I have a rectangle, right? 0, 1, 0, 1. And this function is a product of two functions, right? A product of a function in z and a product of a function in x. So I can take the product of the two integers. Great, so what is that? This is minus cos 1 plus 1, right? And here, what is that? How do I take an antiderivative of this one? Can I take an antiderivative of this? I can, right? This is square root of, or 1 minus d squared to the 3 halves over 3 halves times 2, right? I divide it here, 2 here, and then I take a minus. Z is equal to 1, Z is equal to 0. So I get 1 minus cos 1, that equal 1 is good, so what do I get? I get times 1 over 3. Do you get this? 3 halves times minus 2z, so is that what we got? Is that what we got or not? Did we get this? Could be wrong, let's see. 3 halves, minus 2z. We got this? Yeah? Great. By the way, are we comfortable, I mean I should have asked this long time ago, but are we comfortable with 1D integrals taking an antiderivative, like the antiderivative of these things without doing the u sub? Are we comfortable with this or not? We're not? You're, okay, I mean, in your exam you can take a u sub. The goal is not to evaluate a 1D integral, right? If you feel comfortable, just take a u sub. If you don't feel comfortable with this method, just take a u sub. U is equal 1 minus d squared, and then we'll be good, okay? So now we move on to cylindrical coordinates. Now what are cylindrical coordinates? Suppose I have a point in space. How many coordinates do I have? X, Y, and Z, right? Great. Now, how can I describe x and y? X and y can be described by, if you look at the projection of this one, say project of the xy plane. You get x, y, 0. How can you describe x and y? By polar coordinates, right? So x is r cos theta, y is r sin theta, and z is it. You agree with this? If I give you a point on the xy plane, in space, projectile of the xy plane, what do you get? You get a point in the xy plane, right? You get xy, 0. X and y can be expressed in terms of r and theta. And let's just do this. Let's keep that fixed and express x and y in terms of r and theta. What is r here? R is square root of x squared plus y squared. Okay, so basically, I give you a point on the plane, and I give you its height. I give you r and theta, and I give you the height. Can't you figure out what point exactly? If I tell you r and theta, can you determine x and y? So r and theta will determine x and y. And then is 0. Okay? You see this or not? If I give you x and y, can you find r and theta or not? And then you can find z, and z is given to you. Okay? Is that clear or not? This is just x and y, you replace them by r and theta. Instead of identifying a point by x and y, you identify them by r and theta in the plane, regularly. And then you keep z is equal to z. Now what's the use of this? What does this describe? What's a rectangle in cylindrical coordinates? So let's say 0 theta to 5, an example. Let's pick an example, 0r to what? 1? 0r1. And z is between, let's say, 0 and 5. How do you draw this in the plane, r and theta? In the xy plane, this is a circle of radius 1, a disk of radius 1, do you agree? Everybody, do you agree? This is a disk of radius 1. Now, you allow z to vary from 0 to 5. So what are you doing with these disks? You're just stacking them on top of each other. You see this? What do you get? A cylinder. You see this or not? Yeah? Take a disk and just go up. What do you get? A cylinder. Is a cylinder, what is the height? On high side. And base, that is of radius 1. Of radius, you see that or not? Let's draw this here. Z is 5, and this is you see this or not? I'm still thinking about this. And that change of variables becomes easy to do good. Yeah, I think so. Anyways. Do you guys see this or not? Do you guys see what a cylindrical coordinates are? Great. Now, I want to integrate a function in regular coordinates. X, y, z. Let's say dv will be equal to what? To a triple integral. X will be replaced by what? By r. By what? By r cosine theta. Y will be replaced by what? R sine theta. And z will still be z. Right? Here I have dz, dr, d theta. Right? This is in terms of x. What am I missing here? I'm missing what? A Jacobi. So dv is dx dy dz, let's say. I'm missing a Jacobian. What's the Jacobian here? Del x y z over del x y z over del r theta z in absolute value. Can you tell me? Yes, sir.
Can you remind me of when you know when to use Jacobian technique?
I mean, it's a change of variables, right? So what is dx, dy, dz? It's just the absolute value of the Jacobian times dz, dr, dθ, or dr.
So you're changing dx, dy, dz to dx, dθ? To dr, dθ?
Yeah, so dx, dy, dz with respect to dx, dr, dy, dr, dx, dθ, dy, dθ, dx, dz, dy, dz, dx, dz, dy, dz, dz, dz. Right?
Whatever you do is change the variables to use that.
Exactly. Right? Just like in 2D. Okay? Great. Now what is the Jacobian here? What is dx, dr? What is del x, del r? Del x, del r is what? Is r cosine theta del r. Del r cosine theta is cos theta. Del y, del r is what? Del y, del r is sine theta. Del x, and then del z, del r is 0, right? Del y, del r is sine, del x, del theta, sorry, is minus r sine theta, and then it's r cos theta, and then it's 0, and then 0, 0. You see that? Yeah? Yes, sir.
Sorry, what's that? Next to the Jacobian?
Here?
No. Yeah.
dr theta dz.
Okay, so theta?
Yes. So what do you get here? This is r cos theta, right? You see that? Can you see this determinant? What is that? It's r. You know how to explain the determinant, right? This is just r cos squared theta plus r times squared theta, which is r, right? Yes, sir.
Which one's that has a few different?
And sorry, an absolute value, and an absolute value. Yes. Pardon me? Go ahead. Yeah.
Okay, do you mind repeating like zero to determinant?
Oh, okay. I can do that. I mean, you know, are you guys comfortable in expanding? You know this rule? Plus, minus, plus, minus, plus, plus, minus, plus, minus, plus, right? You know this?
Yeah.
Okay. Expand along this line. This is 0. This is 0, so you only count this one. This is just equal to what? Just the determinant of cos theta. Okay? Yeah? Great. Are we good here? Yes, sir.
Since you're not changing the basis, you're adding the determinant.
So, as your friend noticed here, what is the same Jacobian here? This is it's the same Jacobian as in polar coordinates, right? Is this a coincidence or it's expected? Expected. Are you changing the z? You're just changing x and y and keeping the z fixed. So this is not changing. Very good point. R sine theta z, R, dr, dθ z. Okay. Enough said. Let's do some examples. quick one from the book. Sorry, let's find one, a good one. Where's that? Okay, find the volume. So basically cylindrical coordinates is just polar coordinates, you agree? Just I'm letting the z vary. Find the volume inside the sphere. What is it? What are numbers? 16. And outside the cylinder. What do I have? 1 or 4 or 4? Yeah, sure. Okay, so these are, you can get exam questions like that. These are very nice exam questions. Okay? Things like that are very nice exam questions. They're very quick. And just test that you know the material. Maybe I haven't done, let's see. No, I think it's a fair question, right? Yeah. Should we try this? Did you guys try it or not? We tried it? Did you guys, do you want to take a minute to try it or we just sketch? Let's just sketch. I have a sphere here. Of radius, what is the radius of the sphere? 4. And I have a cylinder of radius 2. This is my cylinder. And this is my sphere. So what is happening here is that I'm cutting my sphere. I'm like, I'm just like, see what's happening, right? So it's like maybe you're drilling like a hole inside the sphere of radius 2. And then I'm just asking you to find the volume. This volume. These are the axes. How would you integrate? Is it clear? Yeah? How would you integrate this one? So Z will vary from where to where? Z will vary from down to up. Do you see that? What is down? Can you solve for Z when Z is negative? Yeah? What is it? It's minus square root of? Yeah? 16, sorry, minus. Great. Now, where will X and Y vary? You've determined Z. project everything into x and y, what do you get about x and y? So if you project this here onto the xy plane, what you get the circle of radius 4, right? And this is my circle of radius 2. Where do x and y vary? Outside the circle of radius 2, right? But I want it inside the circle of radius 4. How can I describe this? By polar coordinates, right? First, let's write this here. Sorry, 16 here. 4. dz dy of dx and y. Now I can switch to cylindrical coordinates or to polar coordinates. It doesn't matter. Which one do you want, cylindrical or polar? Yes.
Does the order matter here?
No, it doesn't. Let's switch to polar or to cylindrical. So theta will vary from 0 to 2 pi. R will vary from 0 to 2, right? From 2 to 4, sorry, right? And then Z will vary from where to where? From square root of 16 minus r squared to minus square root of 16 minus r squared. What is the Jacobian here? R dz dr d theta. This looks nice to integrate. So you have a 2 pi, of course. You can integrate a 2 pi out. And then you have to integrate 2 to 4 square root of 16 minus r squared to r dr. This is easy to integrate. 2 pi 3 halves 3 halves 3 halves 3 halves 3 halves, and then what do you do? Divided by 3 halves minus from r is equal to 4 to r is equal to 2. So you get, this is 0, so you get 2 pi, r is equal to 2, so 16 minus 4 to the 3 halves, what do you get? 12 to the 3 halves, right? 16 minus 4 to the 3 halves, you get 12 to the 3 halves over 3 halves. So you get 4 pi root 3 4 pi over 3 times 12 to 3 halves. Is that it? Does that look good? Yes?
If we wanted to integrate only half of the sphere.
Pardon me?
Half the sphere.
Half the sphere, what do you expect?
Like where does that vary?
So half, which half? Oh, you want to consider x and y are positive, or z is positive?
No, that's one.
X and y are positive. Both of them are positive, or one of them is positive. Right? It becomes more difficult, right? Because it's easier to do half with z being positive. Right? So z will vary from 0 to square root, and then you time it by 2.
This is like half the sphere. And that varies from like
Half the sphere, like where exactly? Which half? The one I colored here.
Yeah.
Okay, sure. Let's do it. So, what's the integral? What do you have to integrate? So, which one you want positive? You said x or y? Both are positive. Sure.
you just integrate like this and then divide by 2.
But you have to divide by 4. So you'll be integrating over here. Right? So theta will be from 0 to pi by 2, and this will be from 2 to 4.
No, if y can be negative.
If y can be negative, so this way. So theta will go from minus pi by 2 to pi by 2, and r will go from 2.
And then
Z will still go the same.
And then it's like what?
You multiply by 2. You multiply by 2.
Ah, okay.
Okay? Is that clear? You're taking half the integral. Well, I mean, it's not always true, right? But in this case, if you take half the integral, you get half the volume. Okay? Yeah. Okay, is that good? Did we get a good answer? Did I get a good answer? Great, awesome. I mean, cylindrical is really different than polar coordinates. It's just polar coordinates. Okay. Now let's move on to a more. Is cylindrical clear? We all know what polar coordinates are. Cylindrical is just like a how do we say just an extension of polar coordinates by just allowing one height variable. Great. Now we'll move on to harder stuff. Spherical coordinates. Okay. Have you seen spherical coordinates before? Physics. If you have taken physics, you might have seen that. No? You haven't seen this in physics? Physics, right? Great, so cylindrical coordinates are very easy to deal with. Now we're going to deal with harder type of coordinates. Not very much harder, but slightly harder. Spherical coordinates. You have a point in the x, y, z plane. Okay? And you define it by x, y, z. This is my x, y, z plane. Here, and I have a point here. Okay? First of all, let me call rho squared to be the square of the distance from this point to the origin. Okay? What is the distance from 0 to x, y, z? It's rho. So let me draw the line here. And then you have an angle. Here that I will call phi. So it's an angle with the z-axis. Okay? Then, how can you describe x, y, z in a unique triplet including rho and phi? So this angle here is really you see this? You guys see this? Yes or no? So you have a point here, right? And then you have an angle. Yeah? Yes, sir.
Would you project it onto the xy plane first?
Yeah.
Again, for each x and each y.
Okay. Very good. So once I project onto the xy plane, what is this height? So here I get x, y, 0, right? This is the point x, y, 0. None of the books do it this way, but I don't think they do actually. Let's see how they do it. How do you get it? There's spherical in this book? Oh yeah, there is. How do you get this? What is this height, Reed? What is this height? What is this? This is Z, right? Now this is a right angle triangle here. What is Z? This is Z and this is rho. Z is, what is cosine phi? Cosine phi is Z over rho. Of course, I'm assuming Z is positive here. Okay, just. So this height here really is rho cosine phi. Then, okay, what is this? This is rho cosine phi. What is this? Rho sine phi, right? This length is rho sine phi. Oh, this is x, sorry. This is y. X. Agree or not? Now, if I call this angle theta, what is my x? I go back to polar coordinates. It's this length times cosine theta. What is y? Y is this length times sine theta. You see that? You guys see that? Do you guys see this or not? Great. Now, just to check that we're good. If you add x squared, y squared, and z squared, what should you get? You should get rho squared, right? Now notice phi is like an angle line. It's phi, theta ranges from 0 to 2 pi. You agree? Theta can ranges from 0 to 2 pi. Phi, where does it range? If you give me a theta, and you give me a rho, if you give me a theta, and you give me a rho, right, phi, where can it range? Where does phi range? 0 to? 0 to? So, 0 to? You have a point here, right? So, if you wanna, okay, this is a bit very hard to see. But I don't know if you can convince yourself that phi ranges from 0 to pi. Can you convince yourself of this fact or not? Say you want a point here. Right? You want a point down here. Okay? Can you pick its projections on the in the YZ plane, in the Z equals 0 plane? You can project it, right? You agree with this? So you really specify theta. You agree or not? Do you agree with this? If you pick its projection, then you specify theta. You saw this, or you see this or not? Pick a point, then you specify its, technically specify rho sine phi, and you specify theta. Now, what are the values of sine phi technically? Sine phi is what should sine phi be? Phi, where will it be from? take it, rho sin phi should be positive, for example. Okay? So phi should be from 0 to pi. That's one way that I see it personally. But in general, phi is more like an angle like this. Right? Like, you know, I can't find it. So phi is an angle like that. So if we're going to reach this point, okay? How can I do it with an angle like this? Just turn here, and then you reach it like that. You see what I'm saying, or not? You don't need to bend your hand. Yes, sir. Oh, you're trying it? So you want to reach the point here with an angle phi. Okay, I'm here. How do you do it? Turn here, right? You'll reach it phi. Did I open it more than 180 degrees? No. I want to reach an angle here, right? The thing is that break your arm, break your elbow, and then go back. No. So I have a, okay, it's easier. I don't know. I want to reach a point here. What do? I just turn, and then I open my arm. Do you see that? So phi, do you guys see this or not? So this is the z-axis, I'm the z-axis, and this is phi. I want to reach an angle phi of the chair here. What do? Do I bend my arm like this? What do? Turn. Did I open my hand more than 180 degrees? No. Do you guys see this now? Let's look at this. Now my rotation is the angle theta. You agree that I'm rotating is theta. So theta, how much time do I rotate? How many degrees am I allowed to rotate? 2 pi, 360 degrees. But how many degrees is my hand allowed to open? 180. You guys see this or not? So if I want to reach the black chair here, what do? Do I just overextend my arm? No. What do? I turn. I chose my theta, right? And then I open my arm. I reach it. So do I ever open my arm more than 180 degrees? No. Now do I ever, can I turn more than, so if I want to reach the can over there, what do? I turn, and I open. Okay? So my hand is opening how many, what is the angle at most my hand is opening? Phi, it's from 0 to pi, and the angle I'm turning is from 0 to pi. Is this clear? Yeah? I hope this makes the picture better. It's a bit hard to see. So phi goes from 0 to pi. Is this a good analogy? Like if you wanna, that you cannot open your hand more than 180 degrees, and but you can turn more than 2. Yes.
Why is 0 included?
Right? 0. If I want to point towards myself, the angle is 0, right? And if I'm pointing towards down, the angle is phi. Right? But theta is 0 to 2 pi is, you include one of them, right? I am here, right? This is the angle 0. What's the angle 2 pi? I'm back, right? Now I'm opening. This is the angle 0. The angle phi is, okay? So really, to remember this, you cannot open your arm more than 180 degrees, but you can turn 360 degrees. This is how I do it. Yes, sir.
Can you explain maybe? I'm not seeing the drawing properly. Y and Z, how is Z like phi equals rho? I'm not seeing that.
Y and Z is phi equals rho.
Yeah.
Okay. This is I and Z, right? This is my I. So Z is, so this is the center. Let's say this is the center, and this is Z. What is the angle here? Phi, call it phi, yeah, phi, okay? So, okay, so, okay. This is not 90, this is phi, okay? And this is Z. This angle is the right angle triangle. This Z, rho, right? This is rho, and this is Z, and this is phi. What is the relation? This is the right angle triangle. Shoulder, finger, right angle. How do you relate these? Rho is Z.
Where's the right angle?
Here. Okay? Okay? Yeah, so this is how I remember it. Your hand can't open more than, yeah, it's 1, 2, Anyway, okay, this is how I remember it. Now, let's do a small check. If I take x squared plus y squared plus z squared, what should I get? Rho squared. So let's do this. Rho squared cos squared phi plus, oh god, it's gonna be so bad. Rho squared sin squared phi, not really. Cos squared theta plus rho squared sin squared phi sin squared theta. Factorize sin squared phi, rho squared sin squared phi from these. What do you get? You get rho squared sin squared phi times cos squared plus sin squared theta. You get rho squared sin squared phi, right? And then you get rho squared. Okay? That's the check that you have it done here. Now, what's the equation of a sphere? The whole point of this is that a sphere becomes a rectangle in this. Right? A sphere. The sphere x squared plus y squared plus z squared is equal to 1. It becomes, what is the equation of that sphere in rho psi, and rho phi and theta? What is rho in that case? This rho is equal to 1, right? Theta is from 0 to 2 pi. And phi is from 0 to pi. Okay, is that clear? Everybody, is that clear? Is that clear or not? Yeah? Great. Now, if I change of variables, if I want to integrate and I want to turn it into spherical, x becomes rho, okay, let's see if I remember this, rho sin phi cos theta. Y becomes rho sin phi sin theta, and z becomes rho cos phi. And then what do I have? I have, what do you want? D phi, d rho, d phi, d theta. What do I have here? I have what do I have when I do a change of variable? I have a Jacobian of x, y, and z with respect to rho, psi, and theta. Great. Let's do this. This Jacobian is going to be bad. I have the absolute value of the Jacobian basically. Let's see. dx0, what is that equal to? dx0, what is that equal to? Sin phi, sin theta, sin phi cos. This is the Jacobian. dx by d rho is equal to sin phi cos theta. Then dy by d rho is sin phi sin theta. Okay, dz by d rho is equal to cos phi. Then dx by d phi, del x by del x del phi, what is that equal to? Minus rho sin phi sin theta, right? No, del x by del phi is rho cos phi cos theta. Del y del phi is rho cos phi sin theta, right? And then z del phi, what is that? It's minus rho sin phi. Great, now del x del theta, what is del x del theta? Is minus rho and minus rho sin phi sin theta. And then del y del phi, wait. Del y del theta is rho sin phi cos theta. And then del z del theta is 0. I'll take this in absolute value. then I'll take the absolute value of this Jacobian. Can I erase this? What do you get? How do you expand this determinant? Along what line? Along the last line, right? You get plus, minus plus, right? Plus, minus plus, yeah. So let's do it. You get cos phi. Cos phi. So what do you get here? You get rho cos squared theta, rho cos squared theta cos phi sin phi, rho squared cos squared theta cos phi sin phi, plus rho, that's a good sign, squared sin phi cos phi, right? Sin phi cos phi sin squared theta. You see what's happening here? Factor out that rho squared cos phi sin phi. You get cos squared theta plus sin squared theta. So this is just rho squared cos phi sin phi, right? Then you have a minus here. So it's minus minus, so it's plus rho sin phi. Let's hope we get something nice. So what do we have? We have rho squared. No, wait, what? Yeah, sure. We have rho squared sin phi cos squared theta. No, what am I doing? This is wrong, right? I explained it along the wrong line. Here, right? So what do you get? You get rho sin squared phi cos squared theta. Plus rho sin squared phi sin squared theta. There is something is there something wrong? So I get rho sin squared phi. No, there is something wrong.
Yeah.
There is something wrong. Are my derivatives okay? My derivatives are okay? Yeah. Let's check the determinants. So cos phi, rho sin phi cos phi cos squared theta, that's good. Plus rho squared sin phi cos phi sin squared theta, that should be good. Then plus rho sin phi, I cancel these two. What do I get? I get rho sin squared phi cos squared theta. Is that good? Is that good? Plus, or I did that. Plus rho sin squared phi sin squared theta. There is something. Not good. Oh shoot. This is del x del theta. No, that's fine.
This is rho sin phi positive.
Where? Here?
In the bottom row.
Bottom here?
Like in the matrix.
Here?
Yeah.
Let's see, what did I differentiate? Del x. This is del x del phi, del z del phi. No, del z del phi is minus rho sin phi, right? Man, what's happening today? Let's differentiate. Del x del rho is sin phi cos theta. Del y del rho is sin phi sin theta. Rho cos phi, so del x del phi is rho cos phi cos theta, rho cos phi sin theta, and then minus rho sin phi. Great. Del x del theta minus rho sine phi sine theta. And y is rho sine phi sine theta, so it's rho sine phi cos theta, and z is 0. What is wrong? There is something wrong.
What is
Because there should be cancellation happening. I mean, let's double check. So I have rho squared cos squared theta, so I have cos phi rho squared sine phi cos phi. Cos phi times rho squared sine phi cos phi plus rho squared sine phi plus rho sine phi. Anyway, it's rho cos squared theta times plus rho sine squared phi. So what do we get? So we get rho squared sine phi cos squared phi plus rho squared sine. This is right. No, this was right all along. Yeah. Rho squared sine phi. This was right. There was no mistake. I don't know why I thought there was a mistake. This is good. So the Jacobian is rho squared sine phi. Phi is between 0 and 5, so sine phi is always positive. Part of it is, yes, I didn't know it had such a complicated structure, but it cancels out very quickly. I mean, this Jacobian, you should do it at least once in your life, okay? And you can tell this is the first time in my life that I'm doing it. So, like, you know, okay, you should do it once in your life. I mean, now I know you're copying, just like how I did it. But you should do it once in your life, okay? There are some exercises that you're going to have to do once in your life. This is one of them, okay? So it's rho squared sine phi. Great. Now, what is the volume of a sphere of radius 8? What is the volume of a ball of radius 8? 4/3 pi a cubed, right? Let's try to derive this in spherical coordinates. Of the ball let's recall that a squared. Let's call this b. I have to integrate 1 dv. Now let's switch to spherical. Spherical becomes rho is equal to a. You agree? This is rho in spherical, right? Rho is equal to a. A is plotted here. Rho is from 0 to a. Theta is from 0 to 2 pi. And phi is from 0 to pi. 1, I integrate 1. In order to switch to 0 d theta d phi, what do I have to add? The Jacobian, which is rho squared sine phi. Very good. And now I can apply Sabini's theorem. I have a product of three functions separately, and theta, rho, and phi. Let's do this. Let's do this. Let's do this. Let's do this. So what do you get? You get rho cubed times, let's say, the theta becomes a 2 pi. Let's put it here. And then 0 to 2 pi, or 0 to pi, sine phi to pi. What you get 2 pi, rho a cubed over 3. Sine phi from 0 to pi, so it's minus cos phi, so it's minus cos phi minus 1, so it's Okay? Did we find this? Is it clear? So in spherical coordinates, the sphere, what does it become? X squared plus y squared plus z squared, or is equal to a squared, becomes rho squared, or rho is equal to a. Okay? Just like in the polar, the circle x squared plus y squared is equal to 5 becomes r is equal to root 5. Here, this sphere becomes rho is equal to a. Okay. Let's do one more. We need to find integral of b. Let's see, of great. Let's find the integral of e x squared plus y squared plus z squared, where b is the ball between the sphere of radius 1 and the sphere of radius 2. What is my region of integration? It's between two spheres, two balls, exactly. You agree with this? It's the region between two balls. Now, how can I describe this region? Rho, where will rho go from? Rho is just x squared plus y squared plus z squared. Rho will go from 1 to 2, right? Agree with this, everybody? Yes? Rho is x squared plus y squared plus the root of x squared plus y squared plus z squared. Rho will go from 1 to 2. Agree so far or not? So I have integral rho goes from 1 to 2. Theta will go from 0 to 2 pi. And phi will go from 0 to pi. What becomes x squared plus y squared plus z squared? Becomes rho squared to the 3 halves becomes rho cubed, right? So e of rho cubed. Now, to change the dv into d rho, d theta, d phi, what do I have to put to take into account the Jacobian? What is my Jacobian? Rho squared sine phi. Bam. Can I integrate this? You can integrate this. So that's 0 to pi sine phi. This is 2. 0 to 2 pi d theta is 2 pi. And then all you have to integrate is e to the rho cubed rho squared. So it's e to the rho cubed divided by 3, right? From rho is equal to 4. This is 4 pi e to the 64 minus d8 over 3. 4 cubed is 60. Oh, from 1 to 2, thank you. 1 to 2 e to the 8 minus e over 3. Is that it? Yeah? Great. Let's do one more. Yes, sir.
Can you start with how you got the e, isn't it? Yeah, thought we had 3 over 2, right? The power of 3 over 2, how does it become rho cubed?
Rho squared for the 3 over 2, what does it become? Okay? Great. Is it clear? Just change up variables, you just integrate. Yes, sir?
The bounds are always 0 pi and 0 to pi?
Well, depends. You're integrating over the entire sphere. What if you're integrating over half the sphere? Right? If I'm telling you, you have to integrate above the plane that is equal to 0. Where does phi range? 0 to pi over 2. Exactly. Now, I had a question, is that how to draw a cone? Okay? I had a good question, is that how do you draw a cone? Now, let's try to draw a cone in spherical coordinates. We've seen that equation of a cone So, let's consider this cone here. Let's write an equation for this cone in spherical coordinates. What is root x squared plus z is rho cos phi, right? You agree? Everybody, do you agree? And root x squared plus y squared, what is that? This is rho sine phi. Okay? If x is rho sine phi cos theta, and y is rho sine phi sine theta, and rho is of course positive, x squared plus y squared would be rho squared sine squared, so rho cos phi will be equal to rho sine phi. What can I do here? I can cancel the rows, right? Let's cancel the rows, provided I'm not at the origin. And I get that cos phi is equal to sine phi. Now, if an angle is from 0 to pi, and its cos is equal to sine, what is this angle? Pi over 4. Thanks. So really, a cone is just phi is equal to pi over 4. This is a cone. Right? You see that? This is how we draw a cone. See what a cone means? So phi is kept constant basically. You keep the angle constant, you keep the phi angle constant, you fix it. So I chose an angle, and you just turn. You see? Yeah? That's a nice way of characterizing a cone in spherical coordinates. It's easier than characterizing a cone in polar coordinates. Okay, in polar it's a bit hard to well, it's not very hard, but it still may take some time to digest how to to characterize in polar coordinates, because it's z is equal to r, right? So z is equal to r is a bit not very easy, but in spherical, you fix your angle phi, right? And then what do? You just turn. Once you turn, you drew a cone. Is that clear? Yeah?
What is
Rho is the distance from x, y, z to 0, 0. So a distance is always positive. Okay? Yeah? Phi is equal to pi over 4, yeah. This is the cone that is equal to square root x squared plus y squared. Okay? Should we do one more? Should we do? Yes. Yeah, this one? X squared plus y squared, what is that? This is just rho squared sine squared cos squared theta plus rho squared sine squared theta. Add them up, cos squared plus sine squared is equal to 1. Then you get rho squared sine squared, right? 5. Now, those are positive numbers, because phi is between 0 and pi and rho is positive. So if you take the square root, you can just remove the squares. Okay? Great. Now, let's do should we do an improper integral in 3D? Let's try to do an improper integral in 3D. As in 2D, what can we say about this? As in 2D, how much time do we have left? 10 minutes. Okay, let's do one. Let's see. What's a good one? Yeah, sure. That could happen. Let's look at this integral. Now I have two problems here. Is my region bounded or not? No. Is my function bounded? I mean, near 0, you don't know what happens, right? At 0, 0, 0, the square root is not defined downstairs, right? You cannot put a square root of 0 downstairs. So really, it's an improper integral. Agree or not? Now, is my integrand positive or not? Is the thing positive? So I can just evaluate my integrals regularly. Just like in 2D, we can evaluate it and see if it converges or diverges. Now, I have x squared plus y squared plus z squared over the entire plane. I'm tempted to use something here. X squared plus y squared plus z squared. Once you see that, you're tempted to use spherical. Tempted to use spherical coordinates. Great. Now I want to integrate on the whole space. So I want to integrate on the whole space. How much do I need to turn? 2 pi. How much do I need to open my arm? Pi. And how much do I need to? How much I need my, to point out? 0 to infinity. My radius goes from 0 to infinity. Right? Very good. So rho will go from 0 to infinity. Theta will go from 0 to 2 pi, and phi will go from 0 to pi. What does the top become? E to the minus, everybody. E to the minus, rho squared. The bottom, what does it become? Rho, yeah. Now dz, dx, dy, what does it become? Rho squared times pi, awesome. Rho squared times pi. Then we're going to have 0 d theta d phi. Can you integrate this? Rho squared over rho, what is that equal to? Rho. So you get rho e to the minus rho squared. Well, so you have a product of three functions over a big rectangle. So what you can do? 0 to pi times pi, what's this integral? This is 2, right? You see that? 0 to pi times pi, this is 2. 0 to 2 pi, 1 d theta, this is 2 pi. And then you have to integrate 0 to infinity, rho e to the minus rho squared, 0. What is that? This is 4 pi. 4 pi, 4 pi, 4 pi what? E to the minus rho squared over 2. Over minus 2. From infinity to 0. What do you get here? What do you get? Yeah. So you get 4 pi times 1/2, right? You get 2 pi. Easy, right? I mean, what is the hardest part in 3D integral? Just setting up the integral. This is always the hardest part. You see, I looked at an example, it looked to me innocent at first, and I was like, I couldn't do it, okay? So you have to think about setting up, you always set up the integrals. So I think I told the people who were attending the review session yesterday that if there's a question that I cannot spot how to do it immediately, then it's not going to be on the file. Okay, so if there's questions where I have to think for like 2 minutes basically, I think it's unfair that I put it on the final. Okay, so it's going to be straightforward in the sense that they should be of the level that you have seen in class. Okay, great. What time is it? 10 minutes. Okay, we have a lot. Let's do more. Yes. The trade example, I couldn't do it. I couldn't do it immediately, right? I mean the trader example. I mean, I'll remove the trader example from the recording because it's an embarrassment, I guess. But so the trader example, what I would suggest, you could try a change of variables. For me, at least, okay, that's one way that I was thinking of it. Replace z by 1 minus z. Okay, if you replace z by 1 minus z, it becomes like that. So all you have to do is find the equation of this plane. And you have to find the area, the volume under this plane in the first object. Okay? You could do it this way. I think it's easier. So, yeah, I think it's easier if you do it this way. I'll try it at home, and I think maybe it's a good answer. So let's try something else. So I want a few people to give me some numbers. A volunteer for a number? 18, okay. 6, and then 8. Okay. Find the volume. Oh, the solid. Plus 64y squared plus. How do you go about such a question? Change of variables, right? Do you guys see this? I want to write my 324x squared as something u squared, right? So what would be by u? U would be 18x, v would be 8y, and w would be 6z. Do you agree or not? You want to integrate, let's call this solid r 1 dx dy dz. You want to switch this to an integral in terms of u, v, and w. You agree? What do you have to take into account before you do that? The Jacobian. So this becomes u squared plus v squared plus w squared is equal to 1. And then what? You integrate 1. What is my Jacobian here? I'll let you check that. Do you want me to give you the answer immediately? The Jacobian is 1, and this is here because u depends only on x, and x depends only on u. So here you can compute the Jacobian 1 by 1. Okay? Or do you want me to compute the Jacobian? Do you want me to compute it? I can compute it. So del x, y, z, del u, v, w, what is that? X in terms of u, x is u over 18, right? So this is 1 over 18, 0, 0, 0, 1 over 8, 0, 0, 0, 1 over 6. Okay? So what is this determinant? This is 1 over 18 times 8 times 6. du, dv, dw. Now, what is this integral? Is this a constant or not? This is a constant, so you can take it out. The integral of 1 du dv, what is du dv w? It's the volume of A inside the sphere. What is that? This is 1 over, this is 1. Okay? You guys see that? You guys see this? Yeah? It's good? Great. Should you do more or that's enough? Yes, sir.
For our software, to go, like with the double.
Double.
Be all that were all the.
Yeah, exactly. Exactly. Let's do one more actually. Let's do one more. Let's do one more. One more.
Can you write down the time?
Oh yeah, sure. Let's do one more. Let's try to integrate this. Yes, sir. Oh, the bound? You're just integrating over the sphere. You can do it in spherical coordinates. If you integrate 0 to pi, 0 to pi, and 0 to 1. Right? And you have to put the Jacobian. Is it clear? Yes, sir.
Can you take up 4 pi over 3?
4 pi over 3. What's the volume of the sphere? This is right? Volume inside the sphere. Okay? Yeah? You should know these formulas. So for example, a nice multiple choice would be find the triple integral over the sphere u squared plus v squared plus w squared is less or equal to 1 dv. You can just say it's 4 pi over 3 by the volume of the sphere. Okay? Things like that you can use. Great, let's find this one. What do you suggest we do here? Pardon me? Change a variable and then spherical. But that could be doable. Yeah, we can do that. But let's try to do it another way. So change a variable, we will have to do. But let's try to split this into, this is a product of three functions, you agree? Yeah? So it's not immediate to switch to spherical. So what do you have? You have the integral from 0 to infinity dz times the integral of 0 to infinity of e to the minus y squared dy. This is an infinite rectangle, right? Minus infinity to infinity of e to the minus x squared dx. Okay? Did we need to switch to spherical here? No. Can I evaluate these integrals? I can by the formula or by the result we had last time. What is this equal to? Square root of 5. So this is square root of 5, right? You agree? The one on the right is square root of 5. Here it's square root of 5 divided by 2. E to the minus y squared is an even function whose integral from minus infinity to infinity is root 5. So when you integrate from 0 to infinity, you get, so you have root 5 here, root 5 over 2. And for the last one, what can I do? I can do a change of variables. So write w is equal to 2z. You get integral from minus infinity to infinity. E of minus w squared. What is dz? dz is dw over 2. Right? And so you get, this is root 5 over 2, right? Integral from minus infinity, or you can just start here. So you get root 5 over 4. What do you get here? You get 5 to the 3 halves over 8. Okay, is that clear or not? W is equal to 2z, right? Is that good? So you get 5 to the 3 halves over 8. So it's not when you see like x squared minus y squared. Try to do many things, okay? Great. So now I'll distribute the midterms.